So as we finished up, I promised that we'd go through VSEPR theory a little bit more, which stands for valence shell electron pair repulsion. This is what leads to hybridization and gives us our shape of molecules, and it's so incredibly important that you be able to process this. All of this sort of goes together, okay? So remember, let's talk about carbon because it's organic chemistry. We should. Carbon has 6 electrons, period. The first shell is 1s2, that's filled, that is not a valence shell. The valence shell, on the other hand, has 4 electrons, so there's 2s2 and 2p2. Well, carbon needs to bond, and it needs to bond in 4 directions that are equal. And the reason why is simple, because you can't have 2 bonds going in the same direction, and molecules like to spread out from one another. Atoms like to spread out from one another. And so what ends up happening is we take these 2s2, 2p electrons that are partially or are filled, and instead we hybridize them. And this is a lower energy state than having one lower energy 2s, and then 3 higher energy 2p's. This also means that we have 4 hybridized valence shells, or 4 hybridized shells, if you will, that are going in 4 different directions. So that's what I mean, it gives rise to the shape. So I like to think on how many things are surrounding an atom. And what I mean by things, I mean like how many either bonds or lone pairs that are surrounding an atom, okay, in different directions. So if we have 4 things that are surrounding an atom, that is a hybridization of sp3. Now, if we have this situation, we have a bond angle of 109.5. If there's no lone pairs, we would refer to that as tetrahedral. If there's 1 set of lone pairs, that's trigonal pyramidal, and 2 lone pairs means that it is bent. So we have 0 unhybridized p orbitals and probably not any pi bonds there. If we have instead 3 things that are surrounding the atom, that is an sp2 hybridization. If there's no lone pairs, that's trigonal planar. 1 lone pair would be bent. So 1 unhybridized p orbital and 1 pi bond is likely. If we have 2 things surrounding an atom, that is sp hybridization. It would be linear, and usually 2 unhybridized p orbitals and 2 pi bonds. So that's usually in the case of a triple bond or 2 double bonds, like CO2, like we just saw. And if we just have 1 hydrogen, then that's not really something that we're going to worry about that much. So this is going to give rise and shape to the molecular polarity, which I'll go over in just a minute. So when we have these double bonds, I just wanted to show you sort of what's going on here. When we have a double bond, what's happening is we have sp2 orbitals that are overlapping in what we refer to as a sigma bond. That's a head-on type of collision. So this right here would be what we determine is a sigma bond, okay? We also have 2 unhybridized p orbitals, 1 from each of the carbon. So remember, when you have a p orbital that's unhybridized, you've got 2 different nodes. And so I did this in different color on purpose. We've got a blue node, so that's like the positive, and the black node, if you will, the negative. And so they have to be sort of aligned that way. And the positive sort of like connects to the positive, and the negative connects to the negative. And that's what we refer to as a pi bond. Okay, so pi bonds are the ones that end up making double and then triple bonds as well. So if you look at the pi bonds, they look like this, and I separated that out for the sigma bonds as well. So more of a head-on type of collision. So triple bonds has one of these sigma bonds in the middle, just like you see here, and then they have two pi bonds. So one would be sort of like we see already here. So I know that it looks like there's three different overlaps, but that's not the case. This is one bond, okay? So that's one bond. If you have something that would be like coming in and then behind the screen that you're looking at right now, that's where another pi bond would be in a triple bond, and it actually looks kind of like a tunnel when you look at the two different pi bonds that are present. So let's look at this in a little bit more detail and talk about some examples. Okay, so let's talk about how molecular shape and polarity go hand in hand. Now, I want to start by talking about the Lewis dot structure of water, and let me tell you, I absolutely love water. I literally have it cut out in wood that somebody got me of a water molecule on my desk. Like, this is very important, okay? So make sure that we know what the molecular shape of water is, because it's probably going to show up somewhere. Oxygen has 6 valence electrons, right? Hydrogen has 1 valence electron, and there's 2 of them in this molecule, so we have 8 total electrons to put it together with. So the Lewis dot structure looks like this. So if you don't understand molecular shape very well, you look at that and you go, oh, well, that's linear. No, it is not linear. Keep in mind that because we have sp3 hybridization around the oxygen, and remember that like when we're looking at a molecule, we're looking in like the geometry, we're looking at the atom that's in the center. So each bond, you would have to look at the one in the center. That has sp3 hybridization. There's 2 lone pairs, which means that this is a little bit smaller than 109.5. This is a bent molecule. That is so very important, because without that, life does not exist. It literally is that important. It does not exist on this planet or anywhere, most likely, without the fact that we have a bent arrangement of water. So here's why, okay? Since we have a bent arrangement, electrons are being pulled towards that oxygen from this direction and towards that oxygen from this direction. So we have a polarity going towards the oxygen, and it's not linear, it's at an angle, which means that the overall polarity of this molecule goes in that direction, okay? It has some directionality to it, which means that this is a very polar molecule. Now look, if it was linear, you all, look, if it was linear and we had an AOH in both directions, we would basically be pulling in both directions in the same magnitude, so you wouldn't actually get any polarity to that molecule. At least not significantly. I mean, you might have more electron density in the middle, but that's not going to form a hydrogen bond. The fact that we have a bent arrangement means that we do. And because of hydrogen bonding, okay, check this out, we have a higher boiling point and melting point for water than even things that are much bigger than it, like H2S. And we have, this is going to actually form like ice that does not sink. That's important for fish to live. This creates capillary action so that plants can live and have water go up through their big trunks or leaves or whatever it may be. Transpiration takes place because of this. There's so many things that are vital because water is bent. So it's very important to consider the molecular shape when we're talking about the polarity of molecules, okay? So why do we need to talk about this as far as polarity and molecular shape and stuff? Well, here's how it goes. Valence shells and what we have in them lead to polarity, right? So Vesper, I would also say, leads to that. Polarity in covalent compounds leads to intermolecular forces. Now that's important. Intermolecular forces affect how chemicals behave, like on big scales. It affects the boiling point, melting point, solubility, and reactivity. I'll finish writing that word. Sorry about that. So one thing that keep in mind when it comes to intermolecular forces are between molecules. It's not something of that molecule. So a lot of times people will say, well, what's the intermolecular force of like CH3OH? Well, they're talking about not just that one molecule. What they're really saying is a whole like beaker full of this stuff. What's the intermolecular force between those molecules? Like lots of those molecules. So sometimes that can be confusing when you're first really trying to master this. So intermolecular forces are not covalent bonds. They're between multiples of molecules. And sometimes it says like, what's the intermolecular force between that? Or sometimes it'll say, what's the molecular force between like CH3OH and H2O? So it'll give you two different molecules and ask you which one, how those two things are connected to each other. So when we have stronger intermolecular forces, then we have higher boiling point and melting point. In general, if you're talking about like compounds that are about the same size, then we have a higher boiling point and melting point. Now, if you've got the same type of intermolecular force, there's different stuff that we have to consider then. So I'm not talking about that. I'm saying in general, okay? So remember, actual ionic bonds are real positive and negative, right? So that's like salts and stuff like that. We have some of those in organic reactions, but we're not going to talk about this as much as you may have in general chemistry. I'm going to skip down to where it says hydrogen bonding. So remember, hydrogen bonding is a special kind of dipole-dipole bond, okay? Hydrogen bonds occur when you have hydrogen that is directly bound to oxygen, nitrogen, and fluorine. Those are the three most electronegative atoms that we have, okay? Next, we have dipole-dipole bonds. So this is where it's like partial positive, partial negative, but you don't have a direct connection to to hydrogen. So if you have like a C-double-O bond, that would be an example of a bond that would be a dipole because we have a slightly negative on the oxygen and a slightly positive on the carbon, okay? I'm going to skip down then to London dispersion forces, or you may have heard this as non-polar types of interactions. So we've got a whole bunch of C and H bonds, or things that are non-polar that are stuck together, and they're, honestly, guys, it's not really stuck that well. It's not. You could talk about like, oh, there's this temporary partial charge at this one moment in time, and it might exist for like a femtosecond, and that's what holds them together. Okay, so we can discuss that. The reality is that generally speaking, the reason why these guys stick together is because they don't have anything else to stick to. And things that are alike tend to gather together, right? So we're talking about things that are like oils. We're talking about things like gasoline, things that have lots of carbon and hydrogen in them, generally speaking, not always, like CO2 is also non-polar, but these are things that that don't really have a partial negative and a partial positive, and so they get stuck. Now let's go back to the two that I skipped. These two, basically those are in-betweens. So we have something between like an ionic compound like NaCl and water. That would be an ion dipole type of bond, specifically ion hydrogen bond, but you get my point. And a dipole-induced dipole is something that's between these two guys. So we have something that's like an oil, and it is in the presence of something that has more of a charge to it, like partial charge. So something that would be like a C-double-O bond. And so that oil might take on it that temporary positive and negative more. And so that's kind of like the in-between situations. There's a lot of in-between situations, and we usually handle that one at a time. But I wanted to give you some examples with that, okay? So in general, if you have two compounds have about the same molar mass, the one with the strongest intermolecular force will have the highest boiling point and melting point. And when it comes to solubility, you've probably heard the terms like dissolves like. What that means is that the more alike the intermolecular forces of the two substances, the more likely they are to dissolve in one another, at least in substantial quantities. So most things will dissolve in something else, but very little of it could actually go in. So if we consider oil and water, just a teeny bit of oil will go into water, and just a teeny bit of that water would go into oil. So we don't really consider that to be dissolved, even though it kind of is, like technically teeny bit. But if we consider like salt and water, salt dissolves much better in water. And so we would say that those are soluble. Okay? Okay, I hope that that's helped refresh your memory on a lot of stuff that we're going to use to learn organic chemistry. I can't wait. I hope that you're excited, and work through some problems on these, because you do need to go back and make sure that you understand these concepts. Okay? Thank you very much.